Yeah. No.
I probably didn't even notice.
Okay. All right, let's get started. So let's get started. Ready? Ready? Ready, guys? Okay. We're going to just take a kind of a detour today and talk about trig. You got a homework assignment I posted yesterday. It's due tomorrow, and we'll be back on track with. We're building on constant rate of change now. We're building piecewise linear functions, and so we are knocking on the door of calc. And we're just going to we're all of a sudden going to be doing calc, and you won't even know it. Okay, so it's not going to be like, okay, now we're starting calculus, because this is all calculus. But in terms of the rigors of it, we're going to be kind of easing into it one idea at a time. So I'm showing 3 circles here, one of radius 1, one of radius 4, and one of radius 6. Is that okay? Are we good? All right, so the question is, I just put a purple bar up on the screen. So what am I representing by that purple bar? We're getting used to these bars, right? What am I representing by that purple bar? Radius what?
Circle 1.
Okay, so the radius of the circle that has? What was that? A radius of 1, right? So, okay. What I'm going to do is I'm going to take that radius and I'm going to maintain its length and just flip it up and make it an arc length. Is that fair? So watch, ready? Like that. And make it an arc length. Did you see that? So it's still the same length as before. I just flipped it up and laid it on the arc. Okay, I'll do it again. Ready? So I'm going to just flip it up there on the arc. Okay? What's the arc length? Oh, is there a question?
Isn't that a radian?
What's that?
Is that a radian?
We're getting there. So, yes, we're getting there. Okay, so what is the length of this arc? What's it? Okay, so it's 1. All right. I'm going to do the same thing again with the circle of radius 4. What am I representing by the blue bar? Trevor?
The radius of 4 for that circle.
For that circle, right. Radius of 4, because that circle has radius of 4. I'm going to take that same thing. What am I going to do? I'm going to flip it up on its circle and make an arc length. Last one. What is the length of the blue arc length? Erica?
4.
4, okay. What am I representing by the red bar? Yvonne? What's that? The radius of 6. The radius of the circle that has radius 6. Same thing. So I'm going to flip it up on its respective circle. Okay, so my question is, what is different about these 3, the purple, the blue, and the red? And can you name at least 2 things that are the same about the purple, the blue, and the red? So take a minute at your table. So what's different about those three curved bars, those three arc lengths? What's different? And can you name at least two things that are the same about those three? Okay, go. Talk at your table.
Yeah, like how much is it?
Yeah.
That's
How about the proportion there and the same as the proportion of circles? Like the proportion of the
Okay, let's hear your ideas. So, easy question first. So, Mason, what's different about those three arc lengths? Yeah, the length of each, right? So we said the length of the purple one is 1, length of the blue one 4, length of the red one 6. Okay, so now I asked you to try to think of at least two things that are the same about those three. So I heard some good ideas, parts of good ideas. Okay, Gianna.
It'd be like the same percentage on the graph, like the circle.
Okay, so they're all showing the same percent of a total rotation of a circle. What do you think of that? That's good, yeah. They all show the exact same percent of whatever percent of the rotation, or what, some fraction of the whole circumference of the circle. Good, what else? Yeah?
We're saying that they're proportional to each other.
So what do you mean?
They're multiples of each other.
Okay. You can say, so some build on that, or say more about that? Fine.
This is how I thought of it. I don't know how it explains it necessarily, but it's all the same degrees, continually going outward, so it has the same slope in that sense. It's all following the triangle.
Okay, so he's saying it's following the ends of these arcs fall on a line? Is that what you're saying?
Yeah.
Okay, so they all fall at the same ray. They all end at this. If we made a ray from the origin, they all end at the same ray. Kind of like this. Anything else you came up with something different, that they're all the same? Is there a way that we can say that their lengths are all the same? Is there a way we can do that? Proportionally the same?
well, if you do, it's one arc length. It's like pi r something. I don't know. Whatever that is.
Forget whatever you learned in the past.
Okay.
So is there a way that we can say that their lengths are the same? Anyone think of a way that we can say that their lengths are the same? This is the key to it. Amy?
Well, I was just thinking like if it's in terms of like how many units of the length, they wouldn't be the same, but they are all respectively the same amount of the radius of the circle. Like each, like the purple one is 1, which is the radius of the small circle.
1.
Yeah, it's 1, and then the middle one is 4, which is the radius of the middle circle, and the same is for the red.
Can they all be seen as 1? Kyle, how?
Because the purple one is 1 radius of the circle.
That's right.
The blue one is 1 radius of the 4 radius circle, and the red is 1 radius of the 6
You
radius
see that?
circle.
Yeah. So arc length in terms of distance is different. But if we use a different measuring stick, like they're talking about, if we use the radius of the circle that they came from, they all have a radius length of 1. All those arc lengths are a radius length of 1. You see that? Okay, so this is the idea of angle. So what we call this, so the angle is formed by these two rays. So I've highlighted the x-axis as called the initial angle, and then this one here is called the terminal angle. And so what is this? So this is what we call 1 radian. This angle. Black. So this angle we call 1 radian. And so then what's the angle shown by this blue arc length? What's the angle shown by it? 1 radian. What about the red arc length? 1 radian. So the question is, and we touched on kind of all the different ways of thinking about what an angle measures. So what is an angle measuring? What does this number 1 represent about those two rays, or about the circles? So there's about 3 different ways to think of it. What did we say? What'd you say, Lizzie?
It's the radius.
Okay.
It's in terms of the radius.
That's right. It's the length of it's radius lengths. That's one way to think of an angle. How many radius lengths of arc length do you get? What's another thing that we said that this angle is measuring? It was the first thing that who said that? Maybe Patrick?
So they're more.
Yeah, so they're proportional. So what was the first person? I forgot the first person. What's that?
Was it like the percentage?
Percentage. Yeah. So a percentage or a fraction of a full rotation. So that's another way to think of angle. These all have the same percent or fraction of their full rotation. So relative length or radius lengths is a way to measure angle. Or think about what we're measuring. We're measuring kind of rotation as percent of a total 1 full rotation. And maybe another way to think of it is in terms of these two rays. Yeah?
Shouldn't it just be the angle between the terminal and the reference line?
What between the two?
The angle between
Right, I'm saying what is angle? I'm saying, so what is that measuring? That's exactly what we're doing. What is that measuring? Think of a door. You can think of it like a door. What about the door are we measuring?
Degrees?
Haven't said anything about degrees yet. What quality of the door are we measuring here? How far it's open, right? So how far it's open. So those are 3 ways to think of what we're doing here. When we say 1 radian, we're measuring how many radius lengths of arc. We're measuring percent or a fraction of the circle. And we're measuring also like how open the 2 rays are. Okay? Those are all 3 ways to think about what is an angle. What it's not is distance. Okay? So if we students tend to think that it's just the distance between the rays. Why is that not correct? Why is the distance between the rays not a way of measuring an angle? David?
Because the distance only works, well, like 1 radian can work for, since all circles are proportional, it works for all the different sizes of circles. So, for instance, in the smaller circle, the distance between the rays is a lot shorter than the distance between the rays.
Exactly.
Yeah.
You move out away from your vertex, what happens to the distance? In the same angle. It just gets larger, right? So it's not the distance across, right? Because that distance grows as you get away. But it is arc length measured in radius lengths. Okay, start again. Okay, so here's my original radius. Now I'm going to do that. what might I be representing now with the purple arc length? David?
2 radians.
That's what that is, okay? So what I did now is I took 2, and I put 2 on there. What do you expect when so I'm going to, here's the blue one, which is the circle of radius 4. I'm going to do the same thing. I'm going to take 2 of those and flip them up on the circle. Can you imagine what you're going to see? What's it going to do, Sterling? And then what about 6? Can you imagine? So what I want you to do for each of these 3, for each of the 3, I want you to tell me what the angle in radians is. Start with the radius. So first, what's the radius of the circle that it comes from? What's the arc length in distance units? And what's the radian measure for all 3 of those? Write those down in your notes or wherever you're doing that. So for each one, I want you to write down. What did I say? The radius of the circle it comes from. The arc length we call S. And the angle in radians we call theta. For all 3 of them. For all 3 of them. You're going to write the radius of the circle it comes from, the arc length, and the angle in radians. This is going to get really cool in a second. If it's not already. Everyone's going to go 9 for 9, right? These are easy questions. Go 9 for 9, 100%. Yep, that's what theta is our kind of our convention for representing the angle in radians. So theta, that's that last thing, theta. I'll even give you the terminal radius. I'm going to call on 9 different people, and we're going to bat 1,000. Okay? So make sure you got them. R is the radius of the circle it came from. S is the true arc length in distance units. Distance units. Arc length. And then theta is the angle in radians. So the S values are different. The distance I want arc length in terms of units on the axis. In terms of units on the axis, that's what I want arc length. So S's are different. I think so. Yeah, I got it. Ready to go? Here we go. See if we can do it. So Ryan,
Yes.
radius of the purple circle.
1.
Okay, we're 1 for 1. S for the purple circle. Jack. S for the purple circle. So the 2, right, sorry. 2. Okay? Theta for the purple circle. Chin. What? How many radians is that? Mickey, did you get it? How many radians is the purple one? $120? Uh-oh. Okay. How about Ben? How many radians is that? 2. What is radians? Radians is, tell me what radians is. Jessica, when we say 2 radians, what is that referring to?
Verbal orbit,
For that purple right there. So why is that angle 2?
because it's the length of 2 radius.
The length of 2
It's 2 radius.
radii. Right, yeah. So it's the arc length of 2 radii. It's the rays that would cut off, 2 radius lengths on the circle. That's what that is. Okay, let's keep going. So Ben, what's the radius of the blue circle?
4.
What is this arc length? Amy, what is the blue arc length in distance units? 8. How many radians is the blue arc length? Zoo. 2. Radius of the red circle. Mason. 6. Arc length and distance units. Megan. 12. Theta in radians. Who's Kyle? 2. Doesn't make sense. So look at this. What is theta? What is theta? In terms of, well, it's 2, but in terms of R and S. Okay, S divided by R. And what kind of computation is that? What's that? Relative size. Talk to me. How is this relative size? It's a quotient, right? Can anyone explain what we're getting at here? John Paul, any ideas?
It just means that no matter what the size or what the arc length is, the ratio will always stay the same. So the theta will always remain constant.
Okay, so you've got a constant ratio. That's true. But what is this? Why am I kind of highlighting this thing of relative size? What is? Yeah.
That's a rate of change.
Okay, but talk to me. Tell me what you're thinking.
You're measuring the arc length in terms of the radius.
Yeah, we're measuring. So we said that quotients are a measure of this quantity. We're measuring arc length, but in what unit?
Radius.
In radius units. Isn't that what we said angle was? Yeah, and so this quotient is kind of reinforcing the fact that we said quotient is measuring the numerator in the units of the denominator. That's what that relative, so 2 is the relative size of what? It's the size of, 2 is the size of what? The arc length relative to the size of the radius of the circle that we used. You see? So it's the length of the arc measured in units of the radius of the circle that arc came from. You see? And that's what quotient is. Relative size. Okay, so I want you to verify that do this, just quickly do this exercise again can I get it on the screen? So you count with me. These are integer numbers of radians. So how many radians is that? You guys are quick, good. And I'm slow. Okay, verify what we just talked about for this angle. Quickly, just verify it. So go through and verify the idea that we just talked about for this angle. Okay, so Brian, right here, Brian. Talk to me about the blue circle.
The middle one.
Yeah, the middle one, blue one.
Its arc is going to be 4.
The radius of this circle is 4, okay.
Its length, the S, is going to be 20 since there's 5.
He said the S is going to be 20 since there is
5 R's, basically.
5 R's that make up this arc, right? 5 radius lengths that make up this arc, so?
But the theta is still going to be 5.
Theta is still 5. And so that 5 comes from, is equal to, using these numbers?
S over
20 over 4, or we're measuring the arc length in units of the radius, which is 4. So if we measure that arc length in the units of radius length, we get 5 radius lengths, and so it corresponds to the angle 5 radians, or openness of 5 radians. Okay. So what I want to do is I'm going to zoom in on the smallest circle. And we can see most of it. Okay, so this circle, the question about this circle is, how can this circle, can you even see the circle in that back? I need a new bulb in that machine. Too bright. So maybe look at this one up here. How can this circle, how can it represent any circle? So think about that. How could this circle represent any circle we want it to represent? David's got a thought. Anybody else? Amy's got a thought. Why don't you just take a second, and if you have a thought, just don't tell the person at your table. So think about it, and maybe have a discussion. How could this circle represent any circle we want it to represent? Okay, go. Take 30 seconds. Okay, so David was first, so we'll have David's reply first. How could this represent any circle?
Because all circles are proportional, so we can use the theta equals S over R to relate any circle to any other circle.
Okay, so the problem with your statement is that quantities are proportional. Circles are objects. Okay, circles are physical objects, so they can't be proportional. Quantities can be proportional. So let's, Amy, I think you had your hand up.
I didn't tell what was saying. I always said like if you put like for all circles at point A being in the origin and point B is just any dot on the arc,
Okay.
the arc of the circle, that quantity has to be the same within one circle in order to make that into and then I can use it.
Okay. Anybody, when you guys thought about it, anybody think about just talking about the radius?
Since the radius is any unit of 1, you can multiply it by anything and still have a similar proportional.
So if this circle was 1,000 centimeters, say this circle's 1,000 centimeters radius. How many radius lengths is that? It's still one radius length, right? If this circle was 0.15 miles, has a radius of 0.15 miles. How many radius lengths would that be in this circle? Still be one radius, you see? So if we think of all circles and measuring circles in terms of their radius length, then all circles are exactly this. From the middle out to the end is always a unit of one radius length, no matter what that distance is, whether it's 2 centimeters or 100 kilometers. It's still one radius. So we can think of any circle as this, and so we call it the unit circle. It's measured in terms of radius length. And the radius length of a circle is always 1, no matter what distance it is. Okay? So what am I representing here? What am I representing there? Please know this. What am I representing right now? She said 1 radian. Megan, you agree with that? I'm representing 1 radian. That's exactly right. And I'm going to leave that mark there. What am I representing now? 2 radians. It's representing 3. Let's see here if I can make this, try to fill up all the screen. Oh. Just a little too big. Okay. How many there? 4? Can't see it? So we'll just leave it right like that. Okay. And then, wish I could get it in between. Stop. Okay, so now I've marked off, these are whole number of radian angles. I've marked off with these thick marks around the circle. Whole radian angles. Okay, so suppose this circle has a radius of 20 feet. Is it a fair representation of the circle with radius 20 feet? Sure, because the 1 would represent 1 foot, 1 radius length, which would be equivalent to 20 feet. How many feet is it? Well, how many feet is this arc length right here? How'd you get 60? How many radius lengths? And each radius length is 20, right? Okay. So, right here. How many, what's the angle right here? About. So tell me the angle in radians that I'm trying to estimate right here. The angle in radians. 4.5. I'm trying to estimate about 4.5. An angle of rotation of this far around the circle is 4.5 radians. Okay, how many feet would that be if the radius of the circle is 20 feet? 90 feet. 4 times. So this is. We could say that. Is this familiar? Every arc length is a constant multiple of its radius. Does that sound familiar? Because 4.5. If I keep that angle constant, 4.5, measuring relative change of the size of the arc length in terms of the radius, then every arc length will be 4.5 times whatever the radius is. That's our constant rate of change thinking, right? Constant rate of change. So fixing an angle is like a constant rate, like Lizzie said. Okay, so if you fix an angle, the measure of that angle is like a constant rate. It's the relative size. And every arc length is that number times the number of radius lengths. Okay, so what I want you to do is, I'm going to give you, there's 6 circles. I want you to just estimate with on each circle the radian measurement I'm going to give you. They're not for everybody. They're extras. Okay, sorry that the numbers are small. I got to change that. But those numbers are by 0.2s. So 0.2, 0.4, 0.6, 0.8, and 1. So here are the angles that I want you to. So each circle is a different angle because we're gonna be doing some more of this. So in the first circle, I want you to estimate. I'll write them up here. First circle, 2.5 radians. Okay, so we can estimate it in 3 ways, or we could show that in 3 ways: as an arc, as 2 rays, and as a point. Do all 3. So as an arc, as 2 rays, and as a point. Always have your initial ray be the x-axis. Always have your initial ray be the x-axis, and so represent it as 2 rays, as an arc, and as a point. All 3.
On one circle, or on
1 angle measure per circle. So 2.5. Yeah, so all 3 on the same, all 3 for 2.5 on that first circle. Right, thank you. And then 0.3. And then, okay, hold on, I'll explain in a second. 4.25, 6.1, -1, -5. Okay, so here's your sheet of paper. And it's got 6 circles on it. Upper left-hand circle only is for the angle 2.5, but you're going to show all 3 representations of the angle 2.5. Upper right circle is solely about the angle 0.3, but show all 3 representations. An arc length, a point, 2 rays. So this estimation, you're just estimating, doing your best. And then compare the, what I see looks 99% good, so take those out and then compare with the people next to you. Okay, so what I want you to do now is, so 2.5 should have looked something like this. Oh no. That's a real shame. Okay. Watch out for that. So, okay, so here's that arc length representation of 2.5 radians. Here's the point representation. Here's the ray representation. Ray, that's called the terminal ray. It's called the initial ray. So we think of the angle opening this way. Positive angle opening that way. Okay, so what we want to do is we want to, for a couple of these, not much time, but we want to estimate the x and y coordinates of the point. So there's the point representation. We want to estimate the x and y. So let's do this together. What do you estimate the x coordinate to be?
Negative
Isabella?
negative 0.8.
About negative 0.8, I agree. Is that what yours comes out to be? Okay, and then what about the y coordinate? About 0.6. So I want you to go ahead and do that same exercise for at least a couple more. I may stop you before you get done, but at least try any circle you want. You don't have to go top to bottom. You can just pick any circle that you want. do a couple more of those. Estimate that y coordinate and that x coordinate of that point representation of the number of radians. Okay, I'm going to stop you. Let's look back at the 2.5. So go ahead and you can finish it later if you want. But let's look at the 2.5. So that 0.6, I could represent that 0.6 kind of like this with a bar, right? That 0.6, that y coordinate, would be like, kind of like that length right there. Agree? 0.6. What are the units of that measurement? That 0.6. In what unit are we measuring that it's 0.06 what? What's that? Radii? This is 0.6 of a radius, right? It's 0.6 of a radius. Okay? This y coordinate of this point, we have a name for that. Anybody know? The y coordinate of this point that we get from 2.5 radians. Know what that is? You've all heard it before, you just didn't know what it was. It's the sine. It's the sine of 2.5. So the sine of 2.5 is approximately what value? 0.6. What is sine? Sine is the y-coordinate, or the vertical distance above the horizontal diameter, measured in? Not radians. Radians is angled, so measured in radii, or radius lengths. Okay? So the input into sine is the angle in radians. And so if sine is a function, it works on 2.5 and it spits something out. Input is angle in radians. The output of sine then is vertical distance above horizontal diameter measured in radii, in radii. That's right. So the units going in and coming out of sine are both radius lengths. You see that? The units going into sine are radius lengths on the arc, and then the number coming out is radius lengths in terms of how high you are above the vertical, did I say vertical? Horizontal diameter. Okay? So what is negative 0.8? That's cosine. Cosine of 2.5 is approximately equal to negative 0.8. What's the input to cosine? What does that represent? What will the input to be? Angle in radians, which is virtually radius lengths, right? So radius lengths go in. That's what radians are. They're radius lengths on a circle. And what comes out? Horizontal distance. So we're going to say to the right, and what's going to take care of the fact that we're to the left? The fact that it's negative. So horizontal distance to the right of the vertical diameter in, measured in radii. Okay, another way to say this is this whole thing, you can think of it as a distance, vertical distance, or you can think of it as the way we started. How did we start getting that 0.6? What did we say? What's that value? What is it? But how did we start getting that 0.6? What did I tell you to find? The y coordinate. The y coordinate on the unit circle. And so this one is horizontal distance to the right of the vertical diameter, x coordinate. That's what sine and cosine are. They're a distance measured in radius lengths, either above the horizontal diameter of your circle, which would be sine, or to the left and right of your vertical diameter, which would be x coordinate or cosine. Okay, so all I want you to do is estimate the sine, just to finish this up, with a little bit, like 5 minutes of homework. Estimate the sine and cosine for all 6 of those angles. Okay, it'll take you 5 minutes. Okay, estimate the sine and cosine for all 5 of those angles that you drew, and we'll just turn that in with your homework tomorrow. So each circle will have 5 things. It will have the representation of arc length, it will have the representation of rays, it will have the representation as the point, and then you focus on the point, and you're going to estimate sine and cosine for the point for each circle. You good? Cool. All right, see you tomorrow. And then we'll turn that in along with the homework that I posted.
The last 2.
It's okay.